So what we're about to do requires a knowledge of logarithms, which I'm assuming all of us have some base knowledge of. Haha, base knowledge, base logarithm has a base. Haha, funny. Okay. Anyway, we're going to talk about going in between logarithmic form and exponential form of an equation. You know that those are inverses of each other. They're inverse functions. It's pretty mathy, which we don't get a whole lot of math and statistics sometimes. It doesn't feel like. Lots of calculations, some formulas, that kind of thing. It is very calculator heavy, so we want to make sure we have a graphing calculator handy. So if you don't have one, make sure that you do. Oh, it's gray, it blended into the desk, sorry. And we're going to go from here. So let me give you a little bit of background before we jump into it. When we do analysis of data, think about inference for a minute, okay? And when we did inference on bivariate data, what was the only shape that we were concerned about? Linear, right? When we talk about linearity of data, would you agree? So when we talk about linear data, we can do some analysis on it. We can do a hypothesis test. We have a lin-reg t-test that we can do to see if two quantitative variables are linearly, it's hard to say, related. We don't have any kind of information about quadratic data or exponential data, logarithmic data, but we know that they exist. Would you agree? I mean, we know that there can be other relationships amongst bivariate data. They don't have to be linear. We just don't have any way to analyze that or any way to do a hypothesis test or any kind of inference unless it's linear. So what we want to do in the statistics world is make everything linear. And so there are ways to mathematically do what are called transformations on data sets that can, what we call, achieve linearity. We can take data that's not linear, maybe apply the logarithm to an x variable or to maybe a y variable or both, and it actually straightens the data out. It's pretty interesting and fascinating why that happens, a little bit beyond the scope of our class, but it's interesting. If you're interested in that kind of knowledge and theory, then that would be something that you would want to kind of delve a little bit more deeper into. But for our purposes, we're going to look at what we can do to straighten out the data and how we can know what to do and then come up with an equation of the data, which I'll get to why I don't think it's really that relevant, but that doesn't matter. Okay, so before we jump into it, I want to make sure we know how to deal with logarithms, okay? So let's just really quickly remind ourselves, I have a couple of examples here of how we could solve for these particular problems. So just remind me for the first example, how do I solve that for, or how do I evaluate that? There's nothing really to solve. E to the power of the natural log of 2. We know it's 2. For those of us who have that practice or know that, do we know why? There's a couple of ways to talk about it. Your calculator does it for you if you're interested in knowing how to plug it in, but why is it true? Because the base of a natural log is what? E, right? So the base of a natural log is E. So if we have E raised to a log of base E, then it's just simply what that power is, right? So it's just 2. Does that make sense what I'm saying? Yes or no? No? Sure. So what if, so I know that the answer is 2. We know, let me see if I wrote it down the next thing. Nope, of course not. All right, let's talk about logarithmic form. So if I said, for example, a to the x power hang on. A to the x power is equal to b. We can convert that, this is called exponential form. We can convert that to logarithmic form by saying log base a of b is equal to x. Do you agree with that? Does this look familiar to you? No? Functions trig people, did you do it recently? You did it last year in functions trig. Okay, well, so it's been a while if you've done it, okay? It's just basically a way for us to be able to solve. Sometimes it's easier to solve the equations when they're in exponential form. Sometimes it's easier to solve if they're in logarithmic form. So you're able to convert and go back and forth in between to be able to solve these types of equations. Okay? So basically what helps me remember is that the base of the exponent is the same as the base of the log. That helps you. And it's always the base to this power is equal to what you're taking the log of. I don't know. Okay? That's something you just have to know, I guess. So when we go back here, I can rewrite this in a different form if I wanted to, right? And we could use that information to rewrite. We can use this power rule or this conversion rule to be able to know that this is log base E, right? So we know that when we're raising that to that power. You can also type it into your calculator. When you type it into your calculator, since you have those handy, and on the AP exam, you can use it at any time. I can never figure out this. Smartboard calculator is hard to read, but E is, I don't know, where is it? Where is it? Oh, second divide 10, thank you. So it's E raised to the natural log of 2, okay? And you do get, in fact, 2. So the calculator will also help you with that, okay? All right, what about this one? This is a little, I don't really like my notation here, but we have parentheses, so to speak. What will we do here? Notice where my variable is. Where is my variable? In the exponent, okay? And so that tells us it's an exponential equation. So if we wanted to solve this, what would be the first thing I would do? Probably not yet, but in a minute. What do I need to get rid of first? The 3 in front. So I would probably need to divide both sides by 3. So if I divided both sides by 3 first, and 76 divided by 3, ugh, okay, that's fine. 25 and a third, that's fine, okay? So at this point, do you mind if I change that? I wanted to make this, I'm not sure, this is an old, you can see it's from 2014. I wanted to make it so that it would equal a power of 2. No. Let's make it, can we make this, hang on. Yeah, can we make this 48 instead? Only, you'll see why in a minute. Can I make this 48? Sorry, there's a reason, which gives you 16. Okay? I want to start off with an easier one rather than jump into the hard. Okay? So at this point, there's really a couple of different ways to solve. One is I can keep it as an exponential equation, and I know that when you have an exponential equation, as long as both bases are the same, then what their powers are must be the same. In other words, if I have 2 to the x is equal to 2 to the 4th power, what does x have to be? 4, right? So if I can somehow rewrite this so they have the same base, then I can just simply set the exponents equal to each other and solve. So that's why I wanted to make this so you could do that. Understand why I wanted to change it to 48? Okay. So if I go ahead and look at this, what power can I write both of these to? I'm glad you answered. I didn't like my question, but yes, that was what I was trying to say. I didn't say it the right way, but yes. So 2 to what power is 8? Okay, 2 to the 3rd, right? So 2 to the 3rd, are we okay with how I wrote that? Yeah? Understand why? Okay? And then over here, 2 to what power is 16? Okay? So they both have the same power, so that means that I can say that. Do you agree? Speak of the devil. You know what my son wants me to do? Can you call me out of school? I had no classes where we did anything. Dude, I'm teaching. I don't care. All right. Oh my God. Every single day this week. Every single day. Mom, we're not doing anything in school. He has 4 AP exams. I'm sorry, you have something to do. Okay. His AP isn't AP Gov tomorrow? Thursday. He didn't take AP Lit. He's got Gov tomorrow, and then he has Physics C next week, BC Calc next week, and what else? Some other computer science next week. I don't know. Stay in school, kid. All right, anyway. So I subtract, so 3n equals 1, n is a third. Are we okay with that? Okay. So one way we can solve equations that are exponential is when they have the same base. Get them so they have the same base. The other way to do that, like if I hadn't changed that to 48, I could rewrite it so that it's in logarithmic form and try to solve it that way, because sometimes that's an additional way to be able to solve it. So just quickly, how do I convert this equation to logarithmic form? Log base 8 of 16, which by the way is simply a number, equals n plus 1. Okay? Are we okay with what I just did there? The base is the base of this. It's this to that power. This is a number. Log base 8 of 16 is simply a number. So it's if you know the change of base formula, it's log of 16 divided by the log of 8. But again, this is all of you. How much do you know about logs? I don't know what your background is. But you can simply just go and type this in. I have to find out where you type it in.
Well, you can just go with log.
Oh, is it just do it with log?
Log.
Mm-mm.
No, log is if you go math.
It's math. Is it all the way down? Okay. I knew it's in the math. There you go. Log base. Thank you. So you have to, if you just hit log, the actual log button on the calculator is automatically base 10. So unless if you have a different base, you have to do it here. So it's log base 8 of 16. And then aren't we just going to subtract 1 from that? And so we do get a third, which is what we got with the other way too. So either way works, either converting to logarithmic form or using it and where you have the same base. Either way works, exponential or logarithmic. The same base is nice when you can rewrite them quickly, but often you can't. So often you have to use the logarithmic form. Hopefully this is a little quick review of that. Are we okay with that? We will come back to this idea kind of at the end of the lecture when we talk about how to write the equation after we've straightened out the data, okay? Remember, our goal is to take data that's not straight and make it straight. Understand? Why do we want to do that? So we can perform hypotheses on them. You guys good? All right, I want to make sure. Any questions I can answer? You sure? hopefully these are the plots that you came up with. Our original data, this is the original one. And then this one was when we did, this was exponential, right? And we said no. What was this one was, I'm not even sure. What was this one? Logarithmic, I believe. And it's a no. And then this is power. Hopefully that's what you got. Really, really straight. So if we look at the power one, let me go ahead and take the log of x as well really quickly to show you. So we know that over here we have the log of L1. And what am I going to be graphing? Okay. This is going to, L4 is x and L3 is y. Would you agree? So I'm going to do L4 versus L3 here. So we're going to say stat plot. And I'm going to go L4 versus L3. Any questions as to why I did it that order? I did this because of how I plugged in the x versus the y. It is to linear, but it's in the other direction. Because you just can't. I would make sure that you do it then. So, resume stat. And we get a pretty straight data set, okay? If I went ahead and found this line of best fit, oh, thank you. I was like, why is the correlation the same? So stat calc, the red, thank you, it's list 3 versus list 4. List 4 versus list 3, that's exactly right. And we're going to calculate. Notice what we get with the correlation this time. Even stronger, right? And if I did a residual plot on this data set, which I could put into L5, am I going too far if I continue? Are we following my thought process if I keep going this direction? Just want to make sure. So we've decided that it's the log of x versus the log of y. So now we're looking at columns 3 and columns 4. Okay? So if we look at our stat edit, over here, this is my x variable and this is my y variable. And if I'm going to go ahead, I went ahead and found the line of best fit that goes through those points. I calculated that line. I had a really strong correlation. If I did a residual plot on list 3 versus list 4, what should we expect to happen? Expect it to be random, right? Because the original residual plot had definitive pattern. So if I go to list 5 and I put the residuals here, what am I going to graph? Which ones am I graphing to get a residual plot? The correct one on the power data set. What's the x variable? Which column was L4? So aren't I getting L4 versus L5? Yeah? We'll just really quickly just get an idea of what the stat plot looks like. So the L4 versus L5. Better than it was, would you agree? Okay? So it's not as random, but it's, I mean, would you agree that the variability is, you're talking about the liner? What's the E stand for in liner? Equal, would you agree that that's half up, half above, half above, half below? I definitely, oh, it's going through below. Yeah, maybe not. But it's definitely better than it was before, would you agree? And the correlation got much stronger. Okay. So, what does that tell us? Okay? So, since we're taking the log of both x and y, okay, we know that we're dealing with the power equation. I agree. So at this point, it wants us to calculate using our log rules, our exponential rules, how to find the equation that was the best fit. Okay? So, if we find the equation, if we go to our calculator and we go to stat calc lin reg, like I just did a second ago, and I do list 4 4 versus list 3, which is the log of x versus the log of y, and I calculate, how come I got a different number? They got negative 6.8, and I got, did I do something wrong? It's supposed to be negative 6.8 there.
Just check and make sure the equation doesn't make or not. When that was,
Let me try again. I think I did.
I'm supposed to.
Supposed to be all 3 on 4. Yeah, that's right. Let me just check something really quick. Are those the numbers you guys got? Can you guys double check me? I guess I'm just trying to figure out why it's saying it's 6.8. We got the right slope. That's good. Alright, well, we can change it. What number does you set out? So we'll just start. Alright, so we got negative 2.96. That's right. Something, obviously, I was typing it incorrectly, which is okay. Oh, you know, they did natural log. It doesn't really matter whether you do log base 10 or natural log, by the way. Okay, power equation. So, we are going to literally take, do you see how I wrote natural log here? You could take log, the log of y. Let me rewrite it under here. So it's the log of y, and I'm just rewriting it with the variable. So it's negative 2.96 plus 1.5 log of x. Okay, just taking the log of both variables. When you have logs in more than one spot, okay, there are some rules where you can combine them and condense the logs. That sounds familiar to you? Sort of, maybe, kind of, could be. You can also just say, there's all different kinds of ways to do this. Would you agree that this is also true? You understand where I had to go with that? The base of this is 10. If it's not there, it's going to be 10 to this power. And I can keep doing rules. There's a lot of ways to go about doing this in terms of being able to condense and retract. We can go ahead at this point and just look at what they did. So we can just say that this is the same thing as this. The sum of 2 logs. If you remember, this is familiar at all to you, hopefully. This is what I call a Baggio. Let me tell you why. Because we have a calculator. And what does the calculator tell you to do? If I have a data set, can I just go to stat calc? I already know it's a power regression. Would you agree? And we're going to do the power regression on list 1 and list 2. And I want us to calculate it. We've already determined by taking the log of both that this is the equation that we want. And notice that's the equation that we get. There's one in the same. That's the 1.5.
Oh, okay.
1.5. Okay. The calculator does the regression for you. The important takeaway from today, is this, okay? What can I do in a data set to straighten it out? First things first, when we looked at this information, when we looked at the original scatter plot looked linear. It had a strong correlation, and the data looked linear. But what told us it wasn't? The residual plot. So then I had to go and say, okay, so it's not linear, therefore, could it be exponential, power equation, logarithmic equation? And what would I do to each of those to be able to straighten it out better? Once we figured out that it was power, in my mind, you could just go ahead and do the power regression on the calculator and get the equation if you needed it. All right? That to me is just as easy, if not easier, to go that route. But what you'll be asked is how to straighten if you're asked anything at all. Okay? So I wanted to, and this I did look, it's chapter 13. You can look at that in your textbook as well. They talk a little bit more about the quadratic and what you would do. You would just be taking the square root of y. So that's the transformation that you would do, and then you would basically square both sides to get y by itself to solve in the equation. So I don't really want to do any more than that. Honestly, with you guys. We have about a half an hour left. I'd like to look at a question 6 that talks about bivariate data. Can we do that? We haven't done many question 6s. They are uncomfortable because they are often things that we have not seen. But I have one copy that deals specifically with bivariate. So since this is bivariate stuff, can we just make that? All right? So I'm going to pause this.